We'll move on to our third speaker. It's Jane Yook, also from University of Melbourne. Actually, she's a PhD student of Emcee, also doing a joint PhD with the University of Cologne and the Research Center in Jülich in Germany. And she will talk about motion extrapolation and the flash-like effect depends on perceived rather than physical speed. Go ahead, Jane.
Okay, can everybody see this? Okay, right.
Yes, we can see.
All right. Thank you, Christoph, for your introduction. And hello, everyone. My name is Jane Yook from University of Melbourne in Australia. And today I'll be presenting a study investigating motion extrapolation using the flash-like illusion. And this ties kind of nicely with his talk previously. So to give you a brief introduction, transmitting and processing visual information takes time, and these delays are intrinsic to the brain and can be problematic for time-dependent stimuli, such as moving objects, because our perception would theoretically lag significantly. And so by the time it takes for the object to reach awareness, it would already be in a new location in the physical world. And a candidate process is that the visual system compensates for neural delays by predicting ahead or extrapolating the position of moving objects so that we can correctly perceive objects as close as possible to their veridical positions. These extrapolation mechanisms can also lead us to incorrectly perceive moving objects, such as the flash-lag effect, in which a flash presented aligned to a continuously moving object is perceived as lagging behind, as we can see here. So in this classic example, the moving bar is essentially extrapolated due to its motion, whereas the flashing bars on the sides are not. Motion extrapolation is based on a neural representation of the object's trajectory, including an estimate of its velocity, so that when an object moves in a predictable motion, we can estimate its anticipated or future position in real time. And this means that motion extrapolation would depend on how fast an object is perceived. So the magnitude of the flash-light effect should also depend on the perceived speed of the moving object, not necessarily its physical speed. And here, perceived speed of an object is indeed dependent on its physical speed, but it is also influenced by other object features, characteristics such as image pattern or luminance contrast, as we will see here today, which can lead to vastly different outcomes. And of course, some alternative explanations of the flash-light effect based on differential latencies or temporal sampling do not rely on such explicit neural representation of velocity like motion extrapolation does. So the aim of the present study was to test this idea uniquely predicted by the motion extrapolation hypothesis and investigate the effect of perceived speed upon the flash-lag effect. So in our circular flash-lag paradigm, we hypothesized that the faster the perceived speed, the larger the extrapolation, and the larger the flash-lag effect. However, if the flash-lag effect does not depend on perceived speed after all, then we should expect no change. So to do so, we used two manipulations of perceived speed. In the first experiment, we compared the flash-lag magnitude when we added static or dynamic noise to the object, to the moving object, and to make sure that the effect that we see is not due to low-level factors. In the second experiment, we compared when the object was shown at high or low contrast. And we also used two types of textures, including filtered noise and square checker patterns, to show that we could see the results across different patterns as well. So let me show you what the stimuli look like. In these videos, you will see a wedge stimulus rotating around the annulus here at a constant physical speed, but our manipulations would alter its perceived speed. So here you will see a wedge in static noise, and then followed by dynamic noise. And the dynamic noise will appear to flicker as it moves. There's the static and then dynamic. Might not be very clear over Zoom, so I'll just play that one more time. So there's static and dynamic. And then on the right side, we have the contrast stimuli. You will see the wedge in high contrast, followed by the low contrast. And obviously the low contrast will be harder to see against the background. Now you can see in the image here that the contrast stimuli don't have a background annulus as the first one, as we wanted to control for participants having to distinguish the contrast between the wedge and annulus in a similar way that they might do with a dynamic wedge on a dynamic annulus. So we just wanted to control for that. That's essentially the low contrast, but you get the gist of it. So observers completed the following tasks in experiment 1 and 2. In task A, they viewed a standard flash lag task where a moving wedge rotates for a randomly chosen duration. Flash appears, the wedge continues to move. Participants judge whether the moving or the flash wedge was ahead. And in task B, they carried out a speed matching task, and they judged whether the reference or the test wedge was faster. Now, using a staircase procedure, we estimated the point of subjective equality to determine the perceived flash lag as well as perceived speed. And this allowed us to see the effects between the different conditions in a very straightforward manner. All right, so moving on to the results. In experiment 1, we have data from 28 observers who completed experiment 1A, 19 observers who completed experiment 1B, and 48 observers who completed both tasks. We were interested in the main effect of the speed manipulation here, obviously. So as you can see, for both texture types, mean PSEs are higher for dynamic noise indicated by the right bars on both sides, relative to static noise on the left. So this indicates that the flash lag magnitude as well as perceived speed increased for our flicker manipulation. We see a similar pattern of results from 7 observers in experiment 2. Mean PSEs are again higher for low contrast on the right, relative to high contrast overall as well. Additionally, we examined whether the dynamic minus static PSE differences of experiment 1 correlated for individual observers, so that larger change in perceived speed would be expected to lead to a larger change in the flash lag magnitude. However, as you can see in the graphs, we did not see a correlation, and this is possibly due to large variability within the individuals. So the results taken together show that both perceived speed and perceived flash lag increased when the wedge contained dynamic noise relative to static noise. and both perceived speed and perceived flashlight increased when the wedge was presented in low contrast relative to high contrast. And the differences in the flashlight magnitude may be explained by the differences in perceived speed of the moving object due to illusory changes using temporal noise or contrast. This is in line with motion extrapolation, which suggests that the flashlight effect depends on an explicit neural representation of velocity. And finally, I would like to say thank you to our time in brain and behavior lab, my supervisors, Dr. Hinze Hogendorn, Dr. Simon Vossel, and Dr. Ralph Feitner, and of course, Neuromatch for the amazing opportunity to showcase this work. Please keep in touch with me if you would like to. I've got my email, my LinkedIn, and thank you all for your attention. I am very happy to answer any questions now or via email. So I'm a little bit nervous, so I'll try my best to answer.
Okay, thank you. Yeah, so if you have questions, post them in the Q&A. Maybe I'll start with one. You basically looked at perceived speed compared to physical speeds also. And if we connect that back to the first talk, to your model with the STDP, where the STDP is basically responsible for creating this, this lag, wouldn't that mean that the perceived speed would somehow have to basically change the STDP? Maybe both of you can comment on that. Because Hinze, you showed that the speed basically through STDP changed the outcome, and then if it doesn't depend on the physical speed but on the perceived speed, then that should have an effect on the STDP, right?
So yeah, so I guess since you're asking the question about the earlier model, I'll just jump in here. Yes, so I guess the motivation for this study was that many of the other explanations for the flashlight don't depend on an explicit representation of velocity. Like the model doesn't, so the other explanations don't need the neural network to know what the velocity of the object was, because it just gets sampled at a different time, and because it's the physical velocity is different, then there's a position difference. Whereas in this case, you're saying, well, the extrapolation does need to know about the velocity explicitly because it needs it for a calculation. And the STDP model I was showing also requires velocity, because we're saying that the velocity, each of these populations is tuned to a specific velocity. So essentially, if the stimulus gets processed and identified as a certain velocity, it will get sent to that channel or to the other channel, if that makes sense. That's our current way of thinking about that. Where in the visual system that happens is completely open to discussion.
Okay, thank you. Then again, we have a question from Jeroen. Do you have a quantitative theoretical prediction for how much the flash lag effect should change for a given change in perceived velocity?
At this stage, to my understanding, I don't think there is a theory other than the model that Hinze mentioned in his talk, where it goes like that. Unfortunately, in our study, we didn't test multiple velocities. We tested for one to see the direct effect. So I think, going forward, that could be an interesting question to look into, and actually seeing, just seeing what the change. Yeah, I'm not sure if that answered that nicely.
Okay, thank you. So we're already out of